Hello, we are ECE Team 2115 and ME Team 35, and our senior design project is on electromagnetic expulsion of a cylindrical body from an outer tube. This project is sponsored by Newark Newport Division.
The way the coil gun works is very similar to an inductor, where the induced current flows through the coil that would generate an electromagnetic field that will propel the sludge forward with a positive exit velocity.
So here you can see the final solution for our design. We're able with this design to take a standard outlet power and convert it into a usable DC voltage for our coil gun. So here you can see the power module. So the power module takes in standard outlet power, 120 volts AC, 60 hertz, and puts it through a rectifier circuit. So you can first see we go through an LC filter and then an isolation transformer to keep the circuit safe. And then the power is then put through a full bridge rectifier in order to turn the negative half cycles of AC power into positive half cycles. From the full bridge rectifier, we can individually charge all of our capacitors using manual switches. Each capacitor can be charged to a max of 175 volts. Switch 4 is attached to a 500 ohm resistor, which can be used to safely discharge any of our capacitors if necessary.
This is the discharge controller. The microcontroller gives 5 volts to the relay that will send 20 volts to the MOSFET gate that will open the source, allowing the current to flow through the coil to the ground that will allow the electromagnetic field to be generated.
The ME team has completed three specific objectives as follows: a comprehensive automated hatch design allowing remote input to open, close, and lock the hatches, a sled design that provides housing and propels the projectile, and fabricated metal spools.
Here we can see a closer look at our hatch design. For manufacturing of the design, we chose to 3D print out of carbon fiber reinforced nylon layered with fiberglass. This material has strength comparable to aluminum at a more reasonable price than machining out of a solid aluminum would be. Once the hatch door is driven closed by the miter gears, a threaded ring consisting of 6 interlocking teeth work to draw the door in, creating a seal capable of holding pressure in excess of 100 psi. A simulated video of the interlocking ring motion can be seen here.
The sled design, made with 3D printed material, consists of two major components. The iron core housed in the back of the sled propels the projectile using the induced magnetic force from the coils, and the rollers contact both the launch tube and the projectile to reduce friction between moving components while the sled is in motion. Here we have a video of a full dry run showing the charging process as well as the projectile exiting.
Tube loaded. Alright. Circuit's going live.
Ready.
Ready, charge, capacitor 1.
Good.
Capacitor 1 fully charged, 140 volts. Capacitor 2, ready to charge?
Yep.
Capacitor 2 charging.
Good.
Alright, capacitor 2, fully charged, 140 volts. Capacitor 3, you ready to charge?
Yep.
Capacitor 3 charging.
$140.
140 volts, capacitor 3, charged. Alright, all capacitors are charged, coils ready.
Alright.
Fire when ready.
Fine.
After inspecting the video in slow motion after the successful dry run, we determined that the instantaneous velocity of the projectile exiting the tube was around 6.25 feet per second. Here we have an example of a less successful wet run.
So in this video, you can see that the projectile barely moves at all. And this is because during testing, we had 2 of our MOSFETs for switching actually break. So we were only using 1 coil during this test. Those MOSFETs had broken down due to an error with our actual coil insulation material wearing off and causing a short, which fried 2 of our power MOSFETs. You can also see in this that we don't have an exit hatch yet, so that is also not currently automated, but those are both things that we are planning on fixing in the near future.